So yes, this is our paper on better practices for domain adaptation. This is with Dali and Timothy Hospedales. So it has changed there and not there. This is good. So what is domain adaptation? Right. So the goal of a domain adaptation model is to learn from a labeled source domain to an unlabeled target domain across a distribution shift. The key point here is it's an unlabeled target domain. And some examples here include maybe we have some X-ray images from hospitals in the UK, which are all labeled with diseases and so on. And we need to adapt that towards a distribution of images from a different country, like Germany. Or we have some NLP model, which is really good at giving us bread recipes, but we want cake recipes. We don't know how to get labels for that. So there's a few different settings within this field of domain adaptation. There's unsupervised domain adaptation, whereby a model has access to both the source and the target domain at the same time when tuning. There's source-free adaptation, where the model only has access to the target domain, and we kind of assume that it's pre-trained on the source domain, and someone just hands us that model. And then finally, the test time adaptation, where the model just sees one kind of stream of test data, and it needs to adapt, validate, and evaluate on that batch all at once. So why is this related to AutoML? Well, so in order to use AutoML type algorithms and techniques in this field, which I believe is pretty necessary, really, because there has been some bad practices whereby even though you're supposed to not have access to target domain labels, in the academic setting, they often sort of sneak in when people tune their hyperparameters and so on. So we have this black box of AutoML approaches, could be HBO, could be NAS. And in order to use this within domain adaptation, we might pass in our data. We might define a compute budget. And then we need to define an optimization metric. Right, but the problem here is that we don't have labels in our target domain, and so we can't use the sort of standard validation accuracy on a held-out validation set. So the question is, what are we going to use as this metric? So in the rest of the talk, if I say validator, that is the same as an optimization metric. It's the metric that we will use to perform sort of model selection within our AutoML pipeline. So there was a paper recently by Musgrave et al., which really highlighted some problems within the field. So state-of-the-art validation methods, or optimization metrics, they find that those were not actually well correlated with the accuracy or the test performance, target domain performance, which poses a problem in that using these metrics did not necessarily lead to any good, well-performing models. And then also the differences between selecting different unsupervised domain adaptation algorithms was much, much smaller than the difference between selecting these validators, right? So we had pretty well-performing algorithms, but actually selecting the best hyperparameters for them or do early stopping with them is a much harder task, it seems. So the aims of our paper is kind of the answer the following. What validators provides the best sort of model selection in the three different settings of UDA, SFDA, and TTA? And then also, are these validators actually good enough to drive a model selection within some AutoML pipeline? And for our method, we decided to perform a big benchmark. So we basically choose hyperparameter optimization to be the sort of AutoML algorithm that we are going to focus on in this pipeline. And so we benchmark a bunch of algorithms in three different settings based off of various types of losses and so on. And then we have a list of validators that are also based on various different types of metrics. For example, top one rank me based off of estimating the rank of your feature matrix in your target domain, or various validators based on the cluster quality if you cluster your predictions. All of these are unlabeled, apart from this final one, which is source accuracy, which is basically if we ignore the fact that there's a distribution shift at all, and we just use the source validation accuracy as a measure of the target domain performance. So we had an HBO setup, like I said. We defined a big hyperparameter search space, including learning rate, epochs, and loss weighting between various different losses that algorithms use. We use random search as our search algorithm here, partly due to the type of analysis that we needed to make. We essentially needed to train them all to completion, and we couldn't really make any decisions that were validator specific. But there are probably cleverer things that we could do there in follow-up work. So we had 10 hyperparameter samples per algorithm. We saved 20 checkpoints through training, and essentially for each algorithm, for each data set, we end up with 200 checkpoints. And it's the job of the validators to rank these checkpoints and then select the best. And then we will then measure how well those models perform. So on to our results. We start with a UDA setting, which again is where a model has access to both source data, which is labeled, and target domain data, which is unlabeled. This is a big table, which has some nice colors that will hopefully help in its reading. So look at the bottom there. The baseline is the cell marked in a gray, or shaded in gray. And this baseline is basically a model which has only been pre-trained on the source domain. And ignoring the distribution shift, we just evaluate on the target test data and then measure its performance. And so we should be able to do better than this model by adapting onto the target domain. Anything in green means that this particular algorithm validator combination resulted in better performance, so successful adaptation. We have the algorithms on the rows there, and then the validators are the columns. The final column says Oracle. That means it's basically the validator which actually has access to these target domain labels which don't exist in practice. So that's the sort of cheating one which we include there just to see what the maximum possible performance of an algorithm is. Overall, what we can say here is that there are some validators which give reliable adaptation, and it's reasonably reliable across the algorithms. And much like we saw in the previous paper that I mentioned, there is more difference between choosing the validators than it is choosing the algorithms. But overall, this table is mostly reproducing what we saw in the other paper. And so we're going to look at the new settings, which we have, which is source-free, where, again, the model only adapts to the unlabeled target domain. And we assume that we are given the pre-trained source-only model. So in this setting, we have a sort of similar situation, but things are a bit more dire, in that the darker red colors here, those cells refer to algorithm and validator combinations, which led to significantly reduced performance compared to the baseline. So we started out with a pretty good performance, but during adaptation and then selecting a checkpoint with a validator, we ended up with really terrible performance. And this ARI, the third validator there, it performed really well in the previous setting, the UDA setting. But in this one, if we were to assume that we can maybe use the same validator in both settings, we would end up with really catastrophic performance. So it really highlights the fact that the choice of validator here is really important. And if we want to be able to do HBO or neural architecture search or something like that, we need to be able to select a validator which reliably gives us adaptation improvements. And then we finally look at the test time adaptation setting, where we only have a single batch of data, and we adapt, validate, and evaluate the model on that. And the standard benchmark within this subfield has been a data set which it's based on CIFAR10, but has added corruptions to it, such as blurring, pixelation, or fog, and so on. So in this setting, which is essentially an artificially constructed domain shift data set, we find that one of the algorithms that we use, TENT, it reliably gives good adaptation performances, it improves upon the baseline, and it doesn't really matter which validator you choose. And in this setting, in fact, the choice of validators is much less important than the choice of algorithm. But then we also look at a more realistic and complex data set. So this is Office Home, which is a standard benchmark in the other two subfields, but not within this one. And we find on this more realistic benchmark that no single combination of validator and algorithm even manages to match the performance of the baseline. And so no matter which combination of these we choose, we end up with reduced performance. And so even performing adaptation in this setting is essentially pointless at this stage. And so this kind of highlights that within the TTA setting, if we look at complex domain shifts, the AutoML paradigm is really, or this setting is not ready for the AutoML paradigm because none of these validators provide a reliable enough validation signal for us to use in our pipeline. So, to conclude, which validator works the best in each setting? We give some suggestions here. So the best validator is dependent on the algorithm and the setting, but for UDA and SFDA, we find that the clustering-based metric V-measure, which had not been used before in the literature, is the best one. And then even though TTA might realistically not be a setting which you should look at, we find that RankMe is nonetheless the best one. And then our validator is actually good enough to realize AutoML pipelines. Well, UDA, I would say yes, but again, be very careful of what validator you end up using. SFDA, much more risky, but it might be possible. TTA, certainly not. And I would highlight work on improving these validators and also perhaps making algorithms that are more conservative and less prone to this kind of catastrophic forgetting of performance. All right.
Time for a couple questions.
So I'm not super familiar with the domain, but for the TTA, you say more validator development is needed. But if you go to the slide, it looks like the oracle is very close to the baseline. So that sort of tells me it's not really the...
Yeah, exactly. It's a good point that I didn't mention. So in the bottom there, you can see at the very end, the oracle does not significantly improve upon the baseline. So that's also showing that whilst the validators don't manage to select any particularly good checkpoints, it's also the fault of the algorithms. They're not really able to significantly improve upon the baseline, even when we sort of cheat and select the best possible versions of them. So yeah, good point.
Any further questions?
Yeah, great talk, really interesting work. So I'm also not really familiar with domain adaptation, but I wonder if, like, in some of these settings like you have on the screen where it's very challenging, can you make use of just a few, like a few shot learning, like a few labeled points in the test setting?
Yeah, so I'm not so familiar whether few-shot learning is something that's much used in the domain adaptation field. But yeah, I think that it would be pretty useful to have a look at that, and yeah, I might search around the literature.
Great. Thank you.
I suppose a natural question to ask is if there's any hope for TTA at all?
So TTA could be kind of decomposed into a SFDA setting. So in the TTA, you kind of get one batch of data, and you could choose yourself, if there is enough of it, to split it into some, train, validation, and test part. And so I would say that is probably the best thing to do, because if we can't sort of think of more fail-safe TTA algorithms, then there's not much hope now.
Okay, please join me again in congratulating Linus and his co-authors.